So I'm pleased to introduce Artie Koeshidayatullah. Artie is a postdoctoral fellow at Stanford. He arrived in January, got started on, in part on a lab-based project, and that was quickly delayed by the coronavirus crisis. But Artie also comes to us with skills in machine learning, and so he's focused much of his time over the past year on using machine learning and image interpretation for geological application. And so he'll talk to us a bit about his work on interpreting carbonate thin sections to understand diagenesis and reservoir quality through that lens. So take it away, Artie.
Thank you, John. So let me reshare my screen. Just want to make sure.
So Artie, we're seeing the presenter view. Oh, okay. It's okay now.
Can you also hear my voice well?
A little bit louder would be great.
Okay, sounds good. So yeah, thank you, John, and hi everyone. So today in this talk, I would like to share with you some of the results from our ongoing collaborative efforts where we use or we apply deep neural networks to optimize and automate geological image analysis. And why we are like really interested to apply this deep learning method to geological image, besides the fact that us as geologists or geoscientists, we love to work with images, we like to visualize things, and we do different kind of image analysis in our works. It's really is the main reason is because we have quite a wide range of types of images and also different scales of images. And when we look at basin and petroleum system model, the way we built this model is somewhat related, that we use different scales of images. For example, we have seismic images to understand or characterize subsurface, different subsurface features, or try to identify different key geological horizons. And then we move on, we have core data or core image from a wellbore that we use it to understand the lithology of the basin, for example. And even we can use it to understand the formation of fractures, how the fractures propagate through these rocks. And if we move even to a much smaller scale, we have a petrographic data where where this information can be really useful to understand the actual component or compositions of the rocks. And also if you want to understand the different mineralogies, different types of cementation, and even porosities. So the way we build our basin and petroleum system model is by combining all this multi-scale information and come up with a cartoon or a model, then use this sort of salient features to represent the actual real world condition. And this concept of using salient features to represent a real world condition is also pretty similar and applicable when we look at the artificial intelligence for computer visions. So in the early days, the way we teach computer to recognize an object in an image, for example, we have a cat here, is by telling the computer with a mathematical language that a cat has this, for example, pointy ears, with chubby bodies, long tails. And then from there, the computer will be able to recognize an object as a cat. And similarly, if you want the computer to recognize a geological object, for example, we have ooit grain here, then we can tell the computer, okay, like ooit has nuclei in the center with surrounded by these different layers or cortices. So when we have this concept of using cartoon or just different salient features to represent a real world object, or for example, we have cat and ooit grains here, this come with certain limitations, because as we know, a simple household pet like a cat, can have an infinite number of variations. For example, if we have this representation for a cat, and how about if we have a cat like this? It means our previous representation doesn't work anymore. Then we need to add more features, different point of view. And how about if the cat is somewhere hidden like this? And even with sort of a funny pose like this, right? And similar when we look at geological objects, for example, with Uit can be in different shape, could be partially dissolved like this, and even sometimes can be heavily fractured and distort the original form. And the things that we don't want to do is to keep adding more information every time we see different images, although they are all belong to the same object or the same class. But instead, we want to teach the computer to be able to learn in a more holistic way and to be able to understand what actually the object is. And the whole idea of using computer vision or using machine learning or deep learning to understand an object is not to actually identify this particular cat or this particular wheat grains, but instead we want the computer to use these different features and be able to generalize, be able to identify cat or wheat grains in general. And this is really where the deep learning comes or deep neural network comes. And what makes deep learning or deep neural networks really powerful for image analysis and also very exciting, that because they have a quite high performance in doing different image tasks, is that it really try to replicate how our human vision system works. So the way human seeing an object is through our eyes, and we transform or transfer this information into our brain, and it's getting processed there through these millions of neurons. And then from there, we will be able to recognize the object, for example, here as a cat. And then this is when we look a bit more detail about the actual architecture of deep neural networks. So when I say deep neural networks, it means you have a different or multi hidden layers. So hidden layers are layers in between your input layer where you look the object, and then your output layer you have for your classification, and in between you have these multiple hidden layers with many neurons that really, when you try to compare this, really try to resembles how our human brain works. And also by having this sort of method, deep neural networks, now we can again try to replicate how human learn. I mean, human learn from experience. So we want also the networks to learn from experience by seeing different kind of variations of data set, and then they will be able to memorize some of these features and later on make a generalization and prediction for this actual object. And also the way deep neural networks work is actually through hierarchical learning. So it's again very similar to how human learn. So we look objects from like simple form like this, the edges, the shape, and then we go a bit more detail, and then combine all these features into a single feature or single object. Then we can start identifying this object. So we get a bit of understanding idea about how this deep learning work and why we want to use deep learning. So now let's start apply this method for carbonate petrography analysis. So the reason we really we focus on carbonate petrography, I mean, as highlighted before by Pulkit, that like carbonate rocks is very important for oil and gas exploration, but also the fact that carbonate system is very complex, and it's often not enough to just look from seismic image, outcrop, even core images to really understand carbonate. So we want to use carbonate petrography as our basic building blocks to do all these, different tasks, and also to really understand carbonate system. So as you can see, by looking at carbonate petrography, you can start understand the components, the different porosity types, mineralogy, and so on and so forth. And we use this information to first classify the lithology of carbonate, and then later on we used it to reconstruct our depositional environments, and we combine all this information to characterize our reservoir and also do basin modeling in a carbonate dominated system. But definitely with carbonate petrography, there are several challenges that we need to overcome. So first, if I ask you a quick question here, I have an example of bryozoan, which is one of skeletal grain in carbonates. And if I ask you to pick between A and B, you know, to identify which one is which one is also bryozoan, when you look at the features, the shape, and the internal features, you may think B is a bryozoan, but it turns out B is a benthic foraminifera, and A is actually bryozoan. And from here, we can realize that first, to do a proper carbonate petrography really requires a domain expertise, in-depth knowledge about carbonate petrology and micropaleontology. And also, just by looking at these two simple skeletal grains, we know that there are quite a lot of similarities between different grains and wide range of variation also. So sometimes it's very difficult to differentiate them, even though you have a lot of experience. And these all are compounded by the fact that to do carbonate petrography is very time consuming and also require a lot of workforce. And the second challenge that I would like to highlight is if you just look at this quite simple thin section where we have a gastropod and a matrix and a micrite, and the study by Lokier and Al-Junaibi back in 2016 asked about 100 geologists to come up with the textural name or the classification of this petrographic image. And as you can see, it pretty much come out with as many as classification that you can name. I mean, this is a very easy sample based on the assessment of difficulty that they made. But then we have quite a lot of variation here, which means as a geologist, we have such a high bias and subjectivity when we try to do facies interpretation. So by looking at these challenges, we want now to use deep learning to optimize some of the processes, make it a more time efficient, but in the same time, we also want to have a process that is less biased and give us a more robust analysis. So there are different types of image analysis that you can do, a deep learning based image analysis. And in this work, we're dealing with a supervised deep learning analysis. When I say supervised means that you need to provide a label or a ground truth for your image or data set, which means you need to tell the computer what your image is. So first we have image classification, where you try to identify a single object in your image. And then second, we have object detection, where you try to identify multiple objects simultaneously. And then you can even move a bit further. Instead of having this rectangular box, you can do a pixel-based classification by doing semantic segmentation. So by doing this method, you can start drawing a mask or like a polygon that really capture the actual geometry or shape of your object of interest. And then in the next upcoming few slides, I will show you how we can use these different image analysis methods to our carbonate petrography and what kind of information can be taken from there. And to do these different tasks, we have compiled more than 4,000 carbonate petrography images. And this is collected from across different geological timescales. And we try our best also to capture the real world variation in carbonate components, carbonate constituents. And from this data set, we have labeled individually more than 13,000 carbonate components, as you can see from this distribution here. And by looking at this training data set that we have, you may realize that there are two things that you want to note. First, we have quite limited data set. We only have like 4,000 and 13,000. But when we talk about deep learning or deep neural networks, usually it requires like millions of data set. And also we have a quite imbalanced distribution of the training data set. And these issues can have a detrimental impact or influence to our training and prediction processes, especially for the learning process of for the machine learning or deep learning. So one method that we use to overcome this issue or mitigate this issue is by applying image augmentation, With image augmentation, you basically apply a image pre-processing method. You manipulate the image with the goal first to increase the amount of data set without actually collecting a new data set. And second, you increase the variation of your data set by, by adding these different features. For example, you rotate the image, you zoom in and zoom out, you stretch the image, and even, you can crop the image. And the benefit of doing this is also you help the computer to learn in a more robust way, because for a computer it's very easy to get confused when they see an object in different orientation or different scales. So that we don't want this to happen. So we want to teach the computer, even though they have different orientation, different scales, they still all belong to the same class. And also by applying this method, we can create a more balanced distribution of data set. So once we done all this, I would like to show you a couple of examples here. So this is an example where we have image classification, where you try to identify a single class or single components in your image. And this is an example where the machine accurately classify the class. We have a mic right here, for example, with bio class, coated grains, and so on and so forth. And when we look at when we try to compare between deep learning and human and geologists, it's actually the accuracy of deep learning is pretty close to experienced geologists. But I would like to draw your attention to this graph here, where I plotted these different categories: geologists with limited experience, experienced geologists, and the deep learning method that we use. And this is the classification rate, or image per second. So as you can see here, with deep learning, it can really give us a much faster analysis while still maintaining high accuracy. So it's almost 5 order of magnitude faster than human. So if you just do a quick calculation, just imagine for 1 second, deep learning can analyze 10,000 images. And if you ask experienced geologists to do this, you probably need to have like days, if not months. And then one of the benefit also with the machine, they don't get tired, right? While human, once they reach to certain limits, and they will get tired, and then they will start make an error there. So this is really one of the main points of using machine learning or deep learning, is to optimize this whole process, to make it more time efficient, but in the same time also with high accuracy. And in this example, I would like to show you also when we apply object detection. So with object detection, the benefit here is that we can just use the original petrographic images. So you don't need to just identify a single object there. And by applying object detection, now we can individually locate different grains and different components in our carbonic photography images. And this is really provide us with a closer approach to how human or geologists describe carbonate petrography. Because when we look at carbonate petrography, we try to identify all these different grains and matrix and cement porosity all in the same time. And by having also these bounding boxes here, the benefit is, or the advantage is, that you could provide with an automatic grain abundance measurements and even porosity measurements. And we took even a step further by trying to apply this method to live petrographic images. As you can see from this video, if you just imagine that we can now integrate this technology to our microscope camera or any kind of camera that you have, then we can start doing this sort of real-time analysis. We can either do it for petrographic images, core images, and even like borehole images. So with this sort of method, I believe we are now we can have sort of a wide range of applications to petroleum exploration, especially for a real-time analysis. And also, probably one of the the benefit of this sort of real-time analysis is that we can now have a much better way to communicate geological data to engineers. So then, now geologists and engineers, they can sit together and, analyze the data together by having this sort of technology implemented. We'll just quickly, show you a couple of different examples here. For example, here try to identify fluids, even with porosity here and there, and different types of grains. So now let's move on to another application. So the next application that we want to to show you is we want to do the automated carbonate phase classification. So as you know, the way geologists or carbonate geologists classify the lithology of carbonate rocks is by looking at the texture of the carbonate rocks, and also by qualitatively estimate the proportion between different grains, matrix, cements, and porosity. And with this qualitative estimation, this really when the subjectivity and the bias come, and we don't want this sort of uncertainty in our analysis. So we applied here image segmentation method. By applying this image segmentation, now we can create an individual mask or polygon for each grains, and separate the grains matrix from the background, which is could be cement and matrix, and we can also separate between porosity and the grains. And by having this sort of mask or polygon, now we can start automatically calculate the proportion of each grain and also measure the grain size. And by calculating the proportion of each grain and also the matrix, we can start having the prediction of our lithophases. And this is very similar to how we do point counting method, and it's definitely much more efficient because this is only takes seconds, if not milliseconds to do it. And also with this method, you can do it in a real-time fashion. And by letting the computer to the machine to calculate the proportion for us by having this different segmentation, and then come up with the predicted lithophases, now we have a less bias and more consistent carbonate lithophases classification. And that's sort of the things that we want to have. And now then, how can we use this data to improve our basin model? So by having a more robust data set or more robust analysis classification of different mineralogy of the carbonate rocks, different grain types, grain size, and also different diagenetic products, degree of cementation, then we can start applying using this information to characterize, for example, the petrophysical properties by looking at the different texture of the carbonate rocks and also the grain size of the carbonate rocks. And then we look at the relationship between porosity and permeability. And then we use this input for our basin modeling. And another thing we can do is to look at, to analyze the thermal conductivity of this rock. Because as you know, the different carbonate minerals, they have a different sort of thermal conductivity. For example, dolomite with comparable porosity values with limestone have a much higher thermal conductivity compared to the limestone or calcite. And then we can again use this information to improve our basin model. And because we can do it in a really in a time efficient way, so then we can also sort of update this basin model in a more dynamic way. So I'd like also to show you in a few slides the couple of ongoing works that we are currently doing. So we are really interested to do 2D to 3D image reconstruction, because as you know before, if you want to create a 3D, reconstruct a 3D image or create a 3D representation of your sample, then you need to do like a CT scan, and it's very costly, it takes time. But now we hope to use a deep learning method, which is first introduced in this computer science field, where they can use deep learning method to use just 2D image of mushroom, and then they create a 3D representation of it. And we want to sort of leverage this technique to our petrography images, and then in order to, and just use, like for example, 2D petrographic image, and then using deep learning method to create a 3D reconstruction of that image. And then we also plan to collaborate with a Giri lab at Princeton, where they have this technology to create thousands of 2D slices from rock slab or core slab and create this 3D reconstruction. And this will be useful to compare and validate our deep learning based results. And by having this ability to create a 3D reconstruction directly from 2D image, there are wide range of benefits, definitely. First, it will be really great for our carbonate reservoir characterization. And then second, it's also very important for our rock physics properties characterization, and also to understand the flow behavior in our carbonate reservoir. And lastly, is also it's very important to know how these different grains is distributed in the 3D space. And we hope to get the results very soon. And moving beyond thin section, the next thing that I'm currently doing, we are collaborating with colleagues at University of Manchester. We look at seafloor pockmarks. In this case, in the Lower Congo Basin, but as you know, seafloor pockmarks is pretty much can be observed anywhere in the world, worldwide. And in this example here in the Lower Congo Basin, we have at least two different origins of pockmarks. First, it's related to fluid escape, which could be related to methane release from gas hydrates or thermogenic hydrocarbon expulsion. And second is related to turbidity or bottom currents scouring. So we want to use different features or parameters of these pockmarks, for example, like the rugosity, the shape, the dimension, and how they cluster together in order to classify them. And using deep learning to automate this classification, it can really give us a more efficient way to classify these different origins of pockmarks. And especially if it's related to the fluid escape, then we can do sort of an early identification by just looking at seafloor map or satellite images and start to understand like what's happening in the basin. For example, if we have fluid escape, could be either we have like oil seepage in that area or like seal bypass system in the subsurface. And also even we can use it for sort of like early exploration stage, because if we have like oil seepage, then we somehow have a working petroleum system in that basin. So this is just a couple of different examples that we are currently doing, but as you know, definitely with deep learning, you can use this method to different kind of images and different scales of images. So this is a few take-home messages that I would like you to note. Hopefully through this presentation, I was able to convince you that deep learning or deep neural networks is really a promising tool to optimize geological image analysis. It can really provide us with a time-efficient, cost-effective, and also like high accuracy analysis. And by applying this deep learning method, it could provide a more robust multi-scale geological input for basin modeling to improve our basin model. And also the application of deep learning to geological images could really add value to our interpretation and also open new research horizon. And lastly, by implementing deep learning, hopefully we can improve the communication between geoscientists and engineers, because now you don't need to have such a expertise to analyze geological data. And with that, I would like to thank all the industrial affiliates and sponsor of BPSM, and also to thank Allegra and other BPSM members for giving me the opportunity to share our work here. And more than happy to take any questions and welcome any feedbacks. And please feel free to email me if you would like to know more about these works. Thank you.
Thanks, Artie. Once again, I don't see any questions in the chat. I know I see one hand up from Allegra. But first I'd like to see if we have any hands up from our affiliates. Feel free to unmute yourself and simply ask Artie a question if you have one.
I'm not sure if people can unmute themselves, but if you click on the ask to unmute button, you can, or type it in the chat.
So while folks are gathering their thoughts, why don't you ask your question, Allegra?
Okay, I think this will actually be relevant. I think this is relevant to the folks online, Artie. Thank you for the talk and for contributing. One of the types of data we have in exploration wells are image logs.
Yeah.
And I have to say that in my experience, the only people that really know how to analyze the image logs are the companies that collect the image logs. And you get some info about what the drilling induced fractures are and what the natural fractures are, but there really isn't a good way to distinguish between those. And I'm wondering if this type of image classification, because we haven't talked about it yet, do you think it could be used in, especially in 3D image logs that we have in some cores?
Yeah. Yeah, I mean, that's a really good point. So definitely we can use this for our image logs, right? And also, especially in 3D, I think recent studies have used many deep learning methods to actually, for example, try to map these fractures, like the actual map, the plane of these fractures, right?
Oh, fabulous.
Yeah, so we can definitely use this method to automate and optimize some of this, data set that we have. But again, as you mentioned, the one who actually understand this image is the one who acquired this image, right?
Well, the people you pay for.
Yeah, okay. So then we somehow need to collaborate with them, because with this type of works, it is a supervised type. So you need to tell the machine first
Well,
what
that's
actually.
true. Yeah. Okay, it's a supervised learning then. Okay. Yeah. Because one of the things I'm thinking in our industry is that, fractures are very important to take advantage of for production. And what we don't do a good job at, or we don't have a handle on, is calculating the extra permeability you get from fracture networks. And to do that, you need aperture, you need length. And so do you think that your image classification technique could go that far in terms of quantifying the lengths of the fracture, maybe even the widths of them? Do you think that's a possibility?
Yeah, again, as you know, it depends on the type of methods that you use. For example, if you use like image segmentation, then it means you can like sort of locate or isolate the fracture itself.
Yeah.
And by having this segmentation, then you can start doing all this kind of quantification.
Fabulous. Okay. One more question, if John will allow me, because I think it's germane to what we're doing. One of the slides that really struck me was when you did the image classification on the ooids, I think it was, and the forams, and how a petrographer, regular eyes can easily get those mixed up. And with the image classification, so getting them mixed up has big implications for depositional environment, right?
Yeah.
And that's one of the things that we need to really think about in basic modeling, but really just in a lot in geology when we're in exploration. And I think that if we can do that, then we can also integrate that with other indicators of, let's say, water depth, like we get from seismic cliniforms, and we get from maybe the global water depth curves through time, et cetera, et cetera. There's a lot of proxies for that, but I'm thinking with your technique, let's integrate that.
Yeah, definitely. That would be really cool.
Thank you.
Thank you, Allegra.
Artie, I have a few questions for you.
Sure.
It may not be relevant, but I was fascinated by your talk. The first question I have is to automate your approach. Is this, do you look at a fixed stage? I mean, in some organic petrography approaches, we have an automated, you can actually automate the movement of the ocular across the slide. So you can sample, millions of pixels across one slide, or are you simply looking at one view per slide?
So if I understand your question correctly, so in carbonic petrography, we use only one view per slide. And then, for example, in the real-time analysis that I showed you, it's actually different compilations of petrographic images, and then we make it in a live or real-time fashion. But again, we can always do it. For example, in sort of your case, by just analyzing first in one view first, and then let the machine to classify that and learn from different examples. And when the machine look at these different views, they will be able to do it, in a real time way.
Yeah, but of course, across a single slide, you may have variations.
Yeah.
So, you might want to think, the first thing I thought about when you were talking about this is an application in AFTA, appetite fission track, to measure those fission tracks in an automated fashion, rather than laboriously sitting there and measuring each one, and training the system to recognize fission tracks that are parallel with the surface of the polished apatite grain.
Yeah. I mean, that's definitely, for me, it sounds doable. And I will be more than happy to discuss in detail with you. And let's,
I've got one last silly question, probably silly question.
Sure.
How do you get an estimate of the grain size distribution from a 2D depiction, from a surface, from a 2D view of the surface of, say, a bunch of ooids?
Yeah.
You have an algorithm that converts the 2D result to a 3D result?
Okay, that's really good point. So that's actually one of the, the ongoing works that we are currently interested to do, because as we know, we have quite limited information when we look at 2D image, right? But unfortunately, that's most of our data set in 2D image. But the next thing, now we can measure automatically the grain size in 2D dimension, 2D image. And we want to extrapolate this into a 3D image by also, using this method that they built in Princeton, where they can reconstruct from thousands of 2D slices and reconstruct the 3D image of that, so that we can know sort of the relationship between the the width and the shape of the grains in 3D space from 2D image.
So I think at this point we should move on to Best's talk.
Sure,
if you have further questions for Artie, send them to us in the chat, and we'll get you answers back in writing. So